So, let us start with what are known as hydrostatic calculations. We already mentioned a little bit about hydrostatic curves, hydrostatic calculations. Okay. Now, the first thing that we need to calculate, the first hydrostatic calculation that you will need to perform is to find the water plane area. Now, in some ways while doing some of the problems I have done lot of this, but I did not mathematically give the exactly do it, okay, the details I did not do last in those problems. So, we will do that in this chapter. So, the first thing you are calculating is the water plane area. Note that it is always written as AW, it is the water plane area, and as you know it is the area at the draft. So, where the water line is cutting the ship, what is the area, that is known as the water plane area. It is twice, right, y is the half ordinate, and y dx will give you the integral y dx will give you the total area, and twice that will give you the both the sides of the ship, port and starboard. So, this is the integral equation for AW. Now, this we rewrite it as okay. This is the same equation, the integral equation, we are writing it in a discretized form. Dx is the distance between two stations is delta L, and this integral is always written as a Simpson's rule or a trapezoidal rule, and this alpha I represents that multiplier, either the trapezoidal multiplier or the Simpson's multiplier. So, it is the same thing. So, it is this integral only. So, this is the first one. So, you are actually integrating this between a water line N1 and N2, the station N1 and N2, and therefore, let us say that it is probably not N2, you can even call it N station equals 1, I equals 1 to some N to avoid confusion, because what we are really doing here is this, means x is going from x equal to a, which is most likely x equal to 0, and it is going up to the total length, L is the length of the ship, dx x is going from 0 to L, the total length of the ship. So, in this case it is going from A to B, it goes from station 1 to the last station, or the station at the aft to the station at the forward point. So, that will give you the total water plane area. Okay, then next one is now you should know this, what is meant by a transverse axis and what is a longitudinal axis. In fact, this part, that is this naming of transverse, we will see which is coming next, transverse moment of inertia, transverse axis, longitudinal moment of inertia, longitudinal axis, it is a little confusing, okay, when you especially first time when you are doing it, you will definitely be confused. So, at the time of exam at least you should be clear, even if you are okay, even if you are confused which is which now, at the time of exam be clear which is this you should know at all times. Means if you have the ship like this, if this is the length of the ship, this axis is always the longitudinal axis and this is the transverse axis, okay. Therefore, what are we doing here? We are finding the moment of the water plane area. This is the water plane area. Let us say this is the water plane area, that means this is the region where the draft is cutting the water line, is cutting the water line is cutting the air, it is reaching the air. So, the moment about a transverse axis, this is a transverse axis. So, what are we doing? We are actually doing finding the moment about this point of the water plane area, okay. This is the first problem. We can do one thing, we take the transverse axis at the origin, let us take this one, let us call this as station 0, which is the origin, the station 0 we will call as origin, and therefore, your moment of this water plane area becomes moment m becomes twice x y dx. It's clear now why it should be x. X is the horizontal distance of each point, and y is the this. Y dx is giving you, if you do integral y dx, you are actually giving the water plane area, and x into y dx is giving you that moment. Okay. So, this again we will write it in the discretized form or the discrete form, that is, so it becomes 2 into sigma, again let us call it from I equal to 1 to n alpha I x I y I delta L. Okay. This can be written like this, and where delta L is representing that dx. So, this is now this you can write as, now how can you write x I? We have seen, let us assume that in the simplest case x I is actually x of each station. You can call it x I, you can call it like this, j I into delta L. Okay. J is the number of station and delta L is that distance between the station. So, 1 into delta L will give you x 1, 2 into delta L will give you x 2, like that. Okay. You are getting x I. So, this equation itself we can write as 2 into sigma I equals 1 to n alpha I j I y I into delta L squared. Okay. This is just some, just taken that delta L outside. So, this becomes your now why is it written like this? It is written like this because this delta L square is a constant, you can be taken outside. So, your idea is to find this summation, and we have already discussed how to find summations, how we are going to draw tables and how do you find the total areas. So, that we will come to next, but that is the goal of writing it like this. This sigma is actually representing that table, summation in that column. So, there is a moment of area. Then how will you get the x coordinate of the center of flotation? We will see this. This is the third one, coordinate. The meaning of the x coordinate of the center of flotation is, I have already told you, center of flotation means the centroid of the area, water plane area. So, you have this area, you want the centroid of that water plane area. So, how will you find it? You will do moment of that water plane area divided by the water plane area, right. Okay. So, that will give you the centroid of flotation. The x coordinate of the center of flotation, let us call it x f, is equal to m x, what we have done here, m x divided by a w. Now, these notations do not change in your in this course, at least do not change it. Let a w always represent the water plane area, m x this moment, because there are lot of m's that come, m x, you will see some m t, different m's will come. So, each of them denoted by the same letter itself. So, this represents 2 into sigma alpha I j I y I into delta L squared divided by 2 into what was a was defined as 2 into sigma alpha I y I into delta L. So, 1 delta L will cancel, 2 will cancel. So, this gives you the x coordinate of the center of flotation. Now, we will do examples that will explain it more clearly, but you can see what do you how do you create the, remember this is what you are calling as LCF, okay, longitudinal center of flotation. This x f is what you are calling as LCF. Now, okay, so this is thing, then this is one summation, summation of one column in a table, which I will draw the table, then it will be clear. Okay, so, this is the expression for x f, then that is what the notation is, that x f is always called as longitudinal center of flotation. So, remember that. Then now there is the fourth one is Now, the fourth one is a transverse moment of inertia of a water plane area. Okay, now this is actually transverse moment of inertia. What is transverse moment of inertia? It is the moment of inertia about, this is the confusing part. Transverse moment of inertia means the moment of inertia about the longitudinal axis. I will explain this again. It sounds a little confusing, but the meaning is that why is it transverse moment of inertia and why is it about a longitudinal axis? It's because of this. Transverse moment of inertia means moment of inertia in this direction. That is obviously transverse, means if this is the longitudinal direction, this is the transverse direction, this is the center line in the middle, that center line is called as a longitudinal axis. Okay. Now, you want the transverse moment of inertia, means the moment of inertia in this direction. So, obviously from where do you calculate? You calculate it based on this line in the center. So, transverse moment of inertia is the moment of inertia about the longitudinal axis. Is it clear, or should I say this again? That is, means what I am saying is, what you need is transverse moment of inertia, means the moment of inertia in this direction. Okay, the ship is like this. Okay, this is the aft of the ship, this is the forward of the ship, and this is one side and this is the starboard side. Then, so if this is the center line, this line is called as the longitudinal axis. So, what do we want? We want the transverse moment of inertia. Transverse moment of inertia is a moment of inertia by multiplying distances in this direction. It is a transverse moment of inertia, means in this direction. So, from where do we take the distance? From the center line. So, it is the moment of inertia about the center line. Is it, should I say? Okay, I think it is clear now. So, this is the transverse moment of inertia. It is the moment of inertia about the center line. So, these things do not, that is why I said it, you keep forgetting this thing, which is, but remember this is the longitudinal axis, there is no doubt about that. Longitudinal and transverse direction should be very clear. Longitudinal axis is clear. If transverse axis is clear, then you can just think transverse axis, transverse moment of inertia has to be in this direction, moment of inertia in this direction. So, you are actually needing the distance in this direction. So, this distance can only be from some fixed line like this, which should be your longitudinal axis. Okay. So, that is the meaning of transverse moment of inertia, like this. I mean, we can draw it here. Let us assume that the ship is this. Okay, this is your ship, this is the center line of the ship, and this is what we are calling as the longitudinal axis. And so, what are we multiplying? We are actually finding the moment of inertia, let us say of small area like this. You take a small area of thickness dx, of length dx, you are actually finding the moment of inertia of this area about this point. So, you have to multiply a y here. Okay. You take the area and you multiply it with y, that is actually going to give you the moment of inertia. Now, again this is always written like this, IT. IT represents transverse moment of inertia about the longitudinal axis, or transverse moment of inertia about the center line. This is the transverse moment of inertia. Okay. Now, looking at this figure, let us say that this distance, let us say that this length is y. Okay, this length is y, and so what will be the moment of inertia of this? Let us consider it to be a means we have taken only dx. So, let us consider it to be a rectangle, okay, because it is a small length. So, d it will be 2y cubed into dx divided by 12. So, it is a rectangle and it is the moment of inertia about this point that you know already. If you are finding the moment of inertia about this, it is this length cubed divided by this length into that length. So, this total length is 2y cubed into dx by 12, that gives you di, and integral of this, that is it will be integral of this 2y cubed by 12 dx, integral of this. So, it will be this, which we will write in a discrete form, which is as it is equal to so 2 cubed is 8 by 12. So, it becomes 2 by 3 into integral y cube dx, which is equal to 2 by 3 into sigma, let us start from I equal to 0 or you can start from I equal to 1, means you are calling it station 0, you are calling it station 1, it is okay, into up to n into alpha I into y cubed y I cubed into delta L. Okay. So, you have I think it is clear, I do not need to explain this again. So,
it should be 8y cubed by 12.
yes, 8 by 3 is 4 by 8 by 12 is 4 by 3, no?
Sir, that one. The second.
Yeah, this is 2y cubed. This one, right? Yeah, this is 2y cubed. So, it is 2 by 3. Okay, then so this is what I was explaining last time, but I did not write down the equation as such. I already told you that how do you find the moment of inertia about the center line of the ship? How did we do it last time? In case I know that there is, I mean, we are covering a lot of portions, we have a lot of things, interrelated things, which kind of sometimes creates confusion. Like for instance, this one, I already told you how you are going to calculate the moment of inertia about the center line, that it was like this that I mentioned there. We will do that, but means you will write a table like this, station 0, station 1, like that, stations like this you will write. Then you will write a Simpson's multiplier 1 4 2 4 or like that. Then you will write then here you are writing the half ordinate cubed. Okay. We were doing a half ordinate cube, and then this is half ordinate cube, and here we are doing a, if you remember, we called it a function of moment, and this was actually given to be, let us name this column 1, this column 2, column 3. So, this column 4 is equal to column 2 into column 3. Okay. I mentioned like this, function of moment. Now, you do this, you get a summation here of different stations, sigma function of moment. So, this I you are getting is I about the center line, which is I about the center longitudinal axis, which is known as the transverse moment of inertia, which is I t. So, this I t is equal to, so this sigma function of moment, I mean this is how I defined there, divided by no into multiplied by it should be 2 by 3 into h. Okay. This is actually the, this you have to, well you can derive it, but you have to remember at least. Okay. This final expression. So, this function of moment is this is really your function of that moment, alpha I into y I cube. Again I will repeat, alpha I represents the Simpson's multiplier or the trapezoidal multiplier, and y I cube, y I is representing the half ordinate, it is half the distance from the center line, half ordinate. So, half ordinate cube. So, that is what we have done here, this function of moment. This function of moment is, what is it, 4 is equal to 2 into 3, 2 is Simpson's multiplier into half ordinate cube, Simpson's multiplier into half ordinate cube, and we are summing it up. We are summed it up and you are multiplying it with delta L, which is h in this case, into 2 by 3. So, this is how you get your moment of inertia about the center line. This you will have to do for the exam, some problem will be there to calculate the moment of inertia about the center line. So, this formula should be firmly in your mind. Of course, it is very easy to derive it, just I guess it is better to just remember this method of derivation, making this rectangle, and you find out the I about this line. Okay. Then okay, now we can have the, as I said, this is the where the confusion can start, that is I will write it 5, the moment of inertia about a transverse axis. This is another one which is slightly different, that is, here we are doing the moment of inertia of the area about a transverse axis. Which is a transverse axis? Suppose this is the ship, okay. Suppose this represents the ship. What we found in the previous section was the moment of inertia about the longitudinal axis, which is called the transverse moment of inertia. Now we are finding the moment of inertia about a transverse axis, means this axis, which is known as a longitudinal moment of inertia. So this is known as okay. So this is known as a longitudinal moment of inertia. Now this is a transverse axis passing through the origin of coordinates. We say origin of coordinates, by origin of coordinates we mean station 0. That is what we usually are calling it as to be x equal to 0. X equal to 0 is, it does not have to be, but right now I am calling x equal to 0 to be the means coordinate system is yours to choose. We can always choose wherever you want, and people do choose it differently. For example, okay, that is the next one, but right now let us assume that x equal to 0 represents the origin. So you are having the moment of inertia about a transverse axis passing through the station through the origin, which is the first station, okay. That is known as the longitudinal moment of inertia, and it is usually designated as Iy. Previously the previous one was It, this one is Iy. Now in your problems, all those problems that you have done, I do not think we have ever done a longitudinal moment of inertia, means what we are doing now, we have never calculated a longitudinal moment of inertia. So just as a aid to help your exam, so that you do not get confused where to take the moment of inertia, you are never going to use this one, means you are never going to do this, you are only going to do the previous moment of inertia, what we have done so far. So of course you have to know it, but know that your moment of inertia always has to be about the center line. Because I have never done any problem dealing with trim. Trim is where this moment becomes important. When you take the moment about this transverse axis, it is actually to do this motion. I have not discussed trim at all, very and we won't be doing most of trim. So you are only interested in heels, so you are only interested in this I. So note that you are going to find always It and not Iy. So for the exam find only It, okay. Then this is defined as Iy is equal to 2 into x into what will it be, x into what was the xy dy, xy dx, okay. It is the second moment of inertia, so it is okay. 2 into x square y dx, okay. So this is equal to, in a discretized form it becomes 2 into sigma I equal to 0 to n, x square can be written as alpha I x I squared into y I into delta L, okay. I mean there is nothing to get confused in this making this thing as discretizing it. That is 2 into, it is this 2 into x is, of course the integral, one new term comes, Simpson's multiplier. So that alpha I into x square becomes x I squared, y becomes y I, and dx is dl, delta L is the distance between two stations. So this is the expression, and to make it slightly simpler, this can be written as 2 into sigma I equal to 0 to n alpha I j I squared y I into delta L cubed. Is it clear? Means xi squared, all we have done here is, so xi is equal to ji into delta L, means the station 2, the distance of the station 2 from the origin is twice the length between two stations. So ji into delta L, so xi square is equal to ji square into delta L square, or ji delta L whole square. Okay, so this is your Iy. Just know this expression anyway, it is important, but you won't be solving it. Then, so this is a longitudinal moment of inertia. Now you can also do a longitudinal moment of inertia. This is about the origin of coordinates, which is station 0. Now you can also find this the moment of inertia about a about which point? The center of flotation. Center of flotation. Okay. Center of flotation, actually you know by now what is the center of flotation. It is the centroid of that water plane area. So initially you had at the beginning of the water plane area, that is at the halfmost point. Now you do not have to do it about this axis I, but you can do it about an axis I which is parallel to this, but at the center of flotation. That is also a longitudinal moment of inertia, and in fact when you just say longitudinal moment of inertia, you usually take it about that axis, about the center of flotation, and the axis through the center of flotation is called a barycentric axis. It is a longitudinal axis, I mean it is a transverse axis. It is a transverse axis through the center of flotation. It is known as the barycentric axis. Now, so this moment of inertia about the barycentric axis, let us call it IL. Okay. Therefore, IL will be equal to Iy minus AW into XF squared. This is just coming from the basic definition of moment of inertia, which says that moment of inertia about any parallel axis is found out by using area of that area, I mean the area of that section into the distance squared. That using that, what is it called? It is a parallel axis theorem or something, no? Yeah. So when you have using that equation, you get I about L, which is I about the centroid. So what is the x of that centroid? It is XF. It is the center of flotation. There is the x coordinate of the center of flotation, which is called as a longitudinal center of flotation, LCF. So that is XF, and once you have that, AW into XF squared. So this formula also it will be useful to remember. Okay. All right. Now we have written a couple of formulas. We can just apply it in one problem, and you will see how it is giving you the different moments of inertia and areas and all that. Now some problem is given such that okay. So I will just, you are told what is the station number, and you are told the trapezoid, okay, you are given so you are given a table which gives you these details, the station numbers, like this. You are given the different station numbers, you are given the half ordinates, which means y, which is this distance. You are given the different half ordinates. Okay, let us name them. this is 1 column 1, this is column 1, this is column 2, column 3. Now, in column 2 we write the trapezoidal multiplier, this time we are using trapezoidal rule. So, you can do it as either as half 1 1 like that or 1 2 2. So, this becomes half 1 1 like that. Okay. So, you have the trapezoidal multipliers. Now, we look at this equation. So, we actually some of the things that we have derived here is, one is this is one we need I y, then we need I t, which is this. Okay. So, our basic purpose in this problem is to find I t and I y. So, I t which is given by this formula, okay, which we have done, and I y which is given by this formula. So, these two things we need now, and okay, you are also asked to find what is LCF and LC, okay, just the LC. So, you are finding I t, I y and LCF, three things. All right. Now, first, so what are the things that you need to do this problem? So, this is what you are given, you are just given the station number and half ordinate. So, first you make the trapezoidal multiplier, that column, then you make a lever. The meaning of lever is actually J I, means the position of that station. Mean it is like lever is actually, what is the distance between stations? It is delta L. So, it goes like this, lever goes like this, 1 delta L, 2 delta L, 3 delta L, 4 delta L. So, this delta L is taken outside and is multiplied later, and it is just lever is just 1 2 3. Okay. So, what we first do is the origin we call it as 0 1 2 3 4, and you will have for different stations you are going to have different levers. That is one column, this we will call as column 4. Then functions of area, alpha I y I. Now, this is to find the total area, water plane area. Okay. So, that you will have to find the water plane area. So, to find alpha I y I, again this is the expression for water plane area, 2 into sigma this thing alpha I y I. So, you see here you have to do alpha I y I summation you have to get. So, you need alpha I y I as one column. So, this will give you the water plane areas. So, this is column 5, then you have okay, where is it now to do, where is I y, that is this thing. To do I y, since you are asked to find I y, you have to calculate alpha I x I y I delta L. I am not sure where I put the next half of it. This is actually can be written as right. I wrote that somewhere. This is the expression for I y. To get I y, you need this expression. That means, what do you need? You need alpha I j I square into y I. That to do that means, see, you need j I square into y I. Therefore, this one, this is the function of moments. This is your 6, column 6. So, what are we doing? Column 6 will be, you have j I, you square j I, you multiply it with the area, you multiply it with the half ordinate. So, alpha I is this one, this column, j I is this lever column squared, into y I is this half ordinate column. So, multiplying they will give you another column of the function of moments. This is to calculate, note that this is to calculate I y. So, in this you will be calculating I y, then we need another column So, what the next one is actually the one you will be using for your exams, that is actually to calculate your IT. I have already told you IT is very important. You are, though this problem we are doing it, you will never be doing IY, you will be only doing IT. So, to calculate IT I have already told you, you will need to do half ordinate cubed, half ordinate cube into alpha I. Okay. So, this is to find IT, which is in fact the most important in this, which you will have to do for exam. So, this is IT. So, half ordinate cube into alpha I. Now, this is actually alpha I into yi cubed. So, this is another column, alpha I comes from this, which is your trapezoidal multiplier, and yi cube is your half ordinate cubed. So, you have another column. So, this is your table. So, of course, to do a problem like this will take 2 or 3 hours, you cannot do it in the exam. Just one small section of it, like just the, if I am given, probably I give you some 4 or 5 stations, 4 stations probably, and I ask you to find the moment of inertia, just to know that you know how to do it, the method. So, that is all I can ask. So, it cannot be this long. This, for example, this problem is very long, you cannot do it. Then, so these are your columns, and once you have these, you have to do, you are given delta L is the distance between stations, whatever it is, that is given. Then AW, let us look at the formulas. Here you have the formula is given 2 this thing into delta L. So, here we do 2 into, in this we have alpha I yi, this summation sigma, okay, this sigma, let us call this sigma 1, this as sigma 2, and this as sigma 3. This represents the summation of all the column, all the elements in this column. This is the summation of all this and summation of all this, sigma 1, sigma 2, sigma 3. So, delta 2 into sigma 1 into delta L. Okay. Just doing this will give you the water plane area of that at that particular draft, and then your next problem is to find, if you are trying to find IT, that will be, again let us look at the formula for IT. IT is this formula. So, this is your formula for IT, okay, this one, it is equal to 2 by 3 into, so this we need. So, in this column we need this one alpha I yi cubed we need. So, this is your alpha I yi cube, which is summed up to get sigma 3, okay, means you have different elements, you have added them up and you are getting sigma 3. So, 2 by 3 into sigma 3 into I think it is delta L, okay. This will give you IT, the transverse moment of inertia, which is the moment of inertia about the longitudinal axis, that is the center line, that is very important. Then, so of course, you have to be able to draw the table, sum it up, and you have to remember this formula also, 2 by 3, this 2 by 3 term and all has to be remembered. So, 2 by 3 into sigma into delta L. So, best thing is not to by heart it, it will be confusing because there are so many such terms. Best thing is to remember the derivation part. So, you just draw that center line, you draw that rectangle, you find the moment of inertia of that rectangle and so on, okay. Then that is IT. Then your next question is to find IY. So, we have to use the formula for IY, this one, which is 2 sigma xi, this one, this is better. So, 2 into sigma alpha I j I squared yi delta L cube. So, 2 into, in this table, this one alpha I j I square into yi, alpha I j I square into yi, this is this column. So, sigma 2 into sigma 2 into delta L squared, delta L cubed, yes, delta L cubed, okay. You do this, you will get your IY. Now, then what else is asked? Okay, so this pretty much this is the different moments of inertia you can find. So, in this we have defined 2 types of moments of inertia. mainly the longitudinal and the transverse, one about the alternately longitudinal moment of inertia about the transverse axis, transverse moment of inertia about the longitudinal axis, and we have also, of course, there is also something known as that about the barycentric axis. The 3 moments of inertia we have defined, of which you have to remember this expression for IT, and you have to know how to make that table. Okay. Then now next one is a little simpler, that is as I said, what is a that is, suppose we want to find out the del, that is the displacement, that is del is equal to there is this is one expression for del, that is the displacement. So, AW is the water plane area. So, you have the total water plane area, and that into this, okay, at each point, at each water plane you sum them out, you will get the volume. So, this also can be written as a discretized form, it becomes sigma I equals maybe 1 or 0, 1 to I maximum, or I about T, means IT represents the I value that is corresponding to the draft, we are summing up till the draft point, into alpha I into AWI into delta T, where means instead of the previous case where we had delta L, we have delta T here, which is the distance between the different water lines, not between different stations now, but between different water lines. Now, I mean, like I told you some time back, you can find the volume in 2 ways. Using the sectional area, you can find, you can sum it up like this, okay, or you can find sum it up like this, either way you get the volume. So, sectional area multiplied by the distance, longitudinal distance, or the water plane areas multiplied with the drafts, both gives you the volume. So, this is how you find the displacement, and next one is now just the extension of this, same as before, that is the moment of this water plane area about the keel. So, about the bottommost point you are finding the moment, we call that the baseline, okay, the keel, you know, keel means the bottommost point, that line we will call it as the baseline. And so, when you are finding the moment about the baseline, you are actually finding the moment like this distance, you are multiplying it with this distance, okay, going up from the bottom, from the keel. So, this is MB, MB is equal to 0 to whatever is the draft, T into AW into dz. It is not z, it should be z actually, z into integral of z into AW into, actually you should change in this, it is not T in the text, it is actually z into AW into dz, that will give you the moment about the baseline. Again this will be, you can discretize it, in this summation will be given by sigma I equals 1 to the last value I T alpha I Z I A W I into delta T. Is it clear? And I mean, it is just, and if you want, you can do one more thing, this Z I can also be replaced the same way as we did last time. We said that Z, for example, we said that X I is equal to J I into delta L, just like that you can have Z I, let us call it J I itself, it is, but note that this is the vertical distance this time. So, J I into delta T, okay, we can write like this. So, this will be, can be written as M B, can be written as alpha I J I A W I into delta T squared, delta T squared, okay. So, you can write it like this as well. Um, now, next and in fact, the last one, that is to find your vertical position of the center of buoyancy. How will you find the vertical position of a center of buoyancy, which we called as VCB? It is the vertical position, vertical distance. It's equal to mb divided by del. Mb is the moment about of that volume about the baseline, and so this VCB will give you the distance from the baseline or from the keel. So, mb divided by del. Mb is calculated here, del is calculated, we just calculated previously. So, using these two you can get VCB. Okay, then so this is all mostly about hydrostatic calculations. Now, just some small things. So, what we have done is we have seen how to basic idea is to calculate the moments, different types of moments, and moment of inertias we have calculated, which is again a moment only, second moment, about origin, about the baseline, etc. Either way you calculate the different moments, you calculate the areas, you calculate the moment of inertia, and you can calculate correspondingly the LCF, LCF, VCF, etc. Okay, as we have seen. Then okay, so these are basically your hydrostatic calculations. We have kind of covered everything. Now, one additional thing that comes another term that we used is we usually call it TPC. It is defined as sometimes it is called as TPI, that is it is actually the same thing, tons per inch immersion, means TPI tons per inch or tons per centimeter, same thing, not same thing, but it is different dimensional systems, either the so now what is the meaning of it? It means that if you have a ship or a body floating in water, how much tons should you add to produce a increase in draft by 1 tons per centimeter, 1 centimeter, means to produce an immersion of 1 centimeter, how much tons of weight should you have to put on the vessel? That is the meaning of tons per inch, tons per centimeter, or if you are talking about inch, it is tons per inch. That definition itself describes it. So, that is the weight required to put to increase the draft by 1 centimeter. Okay, now you can look at it like this. Right. So, this if you increase the draft by delta t, your displacement will increase by this, which is your mass, increase in mass. Now, if you in this case we are going to measure delta, I mean the mass in or weight in, actually then it should be G should be there, no, tons, no sorry, tons is actually kilogram into 10 power or 1000 kilograms is 1 ton. Okay, so delta is in tons, and no, this is correct. Okay, delta is in tons and delta t is in centimeters. That is the only thing to check in this. We measure delta in tons. Always the weight of a ship you never tell in kilograms, you always talk about in tons because it is easier, it is that huge quantity. Then delta t is in given here in centimeters. So, once you have that, when you convert it to your SG units, that is so you will get delta will be equal to this is to do that tons and centimeter. Okay, that conversion, when you do that, this gives everything in meter and newtons. So, this is your expression for delta provided you have it in tons, delta is in tons and del t is in centimeters. So, this is called TPC. Okay. So, your weight is equal to TPC into draft, increase in draft. So, just know this formula, TPC is tons per centimeter immersion. Now, there is another term that comes along with this, that is known as MCT. Okay. Just like TPC, it is MCT is very similar, it is known as one meter. Is it 1 meter or 1 centimeter? 1 meter is it's a large, but it's 1 meter, but it's that's, so it will be a small value. So, the I mean it will be a large value, moment will be large, you have to have a large moment to produce that trim. So, but this is it's defined as MCT. It is, note that this is not heel, this is trim. So, when you have the ship like this, we are saying what is the amount of moment that should be given to cause it to trim by 1 meter. 1 meter, this distance is 1 meter. So, if you draw that figure, let us draw a box, easier to get the angles. So, let us assume that this is a ship that is floating like this. Okay. Now, suppose that it trims, let's draw it like this. So, this is your water line. Now, it trims, let us say there is a moment causing and it trimmed like this. And the total length of the box or the ship in this case is L, let us call it LPP, the length between perpendiculars, it is the LPP. I will just finish this and stop. So, this is LPP, and suppose that you have caused the ship to trim by 1 meter, let us call this angle theta, we are talking about trim. So, we call it theta. So, it has trimmed by 1 meter. Okay, it has moved by 1 meter, and therefore, tan theta is equal to 1 by LPP. Okay, this comes directly. Now, we define something similarly, that is like we defined healing and we talked about the shift of the center of buoyancy in the transverse direction like this, perpendicular, which gives you the metacenter. We have defined things like that. Now, the same concept you can apply to trim also, which is very similar, means it is trimmed like this or like this, and because of it the center of buoyancy will have a longitudinal direction also, means it will be somewhere here, it will be somewhere in this point. So, if the ship heels or trims, the B will move correspondingly. Let us say it trims like this, therefore, B will move like this. The figure becomes exactly similar to that of healing, except that of course, it is a longer distance, other than that there is no difference, and these distances are longitudinal distances, not the transverse distances. So, everything becomes same, like let us say that initially your B is, let us assume G is at the center and B is here. Now, B will move in another direction, B1. This is another metacenter, we call this metacenter as longitudinal metacenter. The other metacenter we were talking about healing, trimming, we call it longitudinal metacenter. The mathematics is exactly the same, there is no difference. Okay, whatever you have done for the previous one you apply here. So, it is not at all different, but note that the length is very small. This is 1 meter, this is the length of the ship, probably 300 meters. So, 1 by 300 is your tan theta, it is very small. So, we are talking about very small values. Maybe I will stop here. So, this is your longitudinal metacenter. So, okay, I will stop here. Okay, thank you.